Welcome. In this video, we are going to go through lesson 3.2. This is going over the fundamental theorem of calculus. And our lesson objective here is to be able to use the fundamental theorem of calculus to find the solution to integrals. So let's start with just a small example considering distance. We're going to let capital M of t be equal to the functions 65t plus 15. Where m is measured in miles traveled on a trip, and t is measured in hours since you started driving. So how far did you travel between hour 3 and 5 is the first question. Well, one way to consider this is to just consider what's the total distance traveled in 5 hours. We could call that m of 5. That would be our total distance traveled after 5 hours, and then subtract away the distance we traveled in the first 3 hours to give us the difference. This would look like m of 5 minus m of 3. So we can go ahead and make those functional values here. This would be 65 times 5 plus 15. And then we can subtract from that 65 times 5, and then, times 3, excuse me, and then add 15. So we have the functional values at these two endpoints. We can subtract from one another and get the distance that has been traveled in between those two endpoints. So if we do so, we should end up getting 130 miles if we add those components up, or really subtract them. Okay, so that looks good. Now let's consider how we would calculate the following integral, the integral from 5 to 3 of m prime of t dt. So we haven't worked with calculating integrals with calculus quite yet, but let's consider just setting this up and seeing how far we can get. So we have the integral from 3 to 5. This is a definite integral. And we have this m prime of t function, which is going to be using the same m function, but again, it's taking its derivative. So if I wanted to find m prime of t, I'm just going to take the derivative of my initial function, which was 65t plus 15. So the derivative here is actually just going to be a constant function, 65. So we can say we're just going to integrate 65 dt. And let's just consider what this integral is actually representing first, and then we'll see if we can calculate it. So an integral is, again, always going to consider the area underneath a function or a curve between the two endpoints given. So this is area underneath the curve. So if I was to graph this, 65 as a function is just a constant line. So here, this is actually telling us our speed is currently just 65 miles per hour. This is our velocity, m prime of t. And if this is our t axis, we can say that we want to consider, well, what would the area underneath this constant horizontal line be from 3 to 5? If we walk these 3, 4, and 5, there's 3, there's 5 on our number line. We're just finding, again, the area under the curve, which happens here to be just a line from 3 to 5. So in other words, this shaded region right here. So notice this is very similar how we considered the beginning of lesson 3.1 when we considered the area underneath some velocity curve. We could see that this creates a rectangle obviously not to scale, but we have a height of 65 and a width of 2 here, which would actually give us the same total of 130 miles traveled. So we have the same idea going on, that the integral here of the velocity function, or the area underneath this velocity function, is the same as the total distance traveled between our two endpoints. So one conclusion that we could make here for this specific problem could be the following, that the integral from 3 to 5 of m prime of t dt is equivalent to what we just found in part A. That was the functional value m of 5, that's the first endpoint, minus m of 3, that second endpoint. And that's what actually we call the fundamental theorem. That's developed straight from something like this, where we're considering what's the total distance traveled between 2 points. So more generally, we can consider now the fundamental theorem of calculus. And this works for any function that we take an integral of. So let's consider that together. And I'm going to highlight this fundamental theorem. So fundamental theorem says if we have an integral from a to b of a function f of x dx, that is equal to what we'll call capital F of b minus capital F of a, where capital F prime of x is equal to the original little f of x. We call capital F of x the antiderivative of f of x, or we can consider f of x the accumulation or accumulated area under the f function. So if we were to draw a picture here to consider this fundamental theorem again, if we started with some f of x function, and consider the area underneath this f function from a to b, we would be considering, again, the area that is accumulated underneath this curve. So just to draw a little bit out here, and I'm going to actually extend this function. Let's say that this function just stops right here and goes on. We can consider these two quantities, the capital F of b. This is the accumulated area to the left of x equals b. Let me write that out. This would be the accumulated area to the left of x equals b. So if I considered drawing this out, maybe we'll put this in blue here. This would be the shaded region that would be trapped here. In a similar fashion, we could do the f of a function, capital F of a, that's the accumulated function at a, the accumulation function at a. This is the accumulated area to the left of x equals a. And again, we'll put this in color here just to show the difference. This area would be the accumulation to the left of a. So we'll notice that if we take the difference of these two areas, capital F of B minus capital F of A, which is the solution to our problem, this leaves the area just highlighted in blue here without the red. So this area underneath the curve just in this blue area, which would be just the area in between A and B. So visually, that's what we're finding is the difference of these two accumulation values, capital F of B and subtracting capital F of A. So let's consider using this fundamental theorem of calculus with a couple examples. We have the integral from 3 to 7 of x squared plus 3x minus 1 dx, where we are given capital F of x, the antiderivative, on the right. One thing that we could kind of check at this point is, well, could we check that f prime of x is actually equal to, or capital F prime of x is equal to f of x? Could that be true? Well, certainly can check that. We could say that f prime of x, or capital F prime of x to be specific, if we took its derivative, we'd have 3x squared over 3 plus, we'll have 3 times 2x, and then divided by 2, and then finally minus 1. Looking at the simplifications here we can do, I think we do find that this will simplify down to our total. So that would be f prime of x is equal to x squared plus 3x minus 1, which happens to be the function that we're integrating. So if we consider the fundamental theorem of calculus would tell us that this integral is equivalent to the accumulation function at 7, that's our upper endpoint, subtract our lower endpoint, capital F of 3. So go ahead and take a moment to fill this one in. You could pause the video at this point and consider what would capital F of 7 minus capital F of 3 be. I'll give you guys a moment to do that, and then we can come back to the video with a solution. All right, so we have our result here, at least shown out here. If we go to simplify our evaluations here, we should get a value of 161.3 repeating if you put that in your calculator. If we do that 161 with 3 repeating, this would be equivalent to, if we put that into a improper fraction, that would be 484 over 3. So there's our exact result, and then maybe a decimal approximation. 161.3 would be that area underneath the curve. Let's go ahead and take a look at part B. We have another function to consider. The integral of from 1.5 to 17 of 1 over x dx, where capital F, the antiderivative of f, is going to be the natural log function. We can verify this as well by considering the derivative of capital F. So if we consider that derivative of capital F, natural log, we know, is just going to have a derivative of 1 over x. And so that certainly matches what we have inside the function. So that gives us kind of a clue of how we're going to consider taking these antiderivatives, just a derivative in reverse. So with that antiderivative, we consider what is the f of 17 subtract capital F of 1.5. So in this case, the capital F is just the natural log function. So we can say that's the same as natural log of 17 subtract the natural log of 1.5. That's the only part of the function. If we take a look and put this into our calculator, we'll round to a couple decimal places here. This would give us an approximate solution of 2.43 if we put that to 2 decimal places. The last one we'll take a look at considers here part C. We have the definite integral from 0 to 4 of x minus 1, and we have its antiderivative, capital F of x, in the problem as well. Let's just verify that capital F one more time with the derivative. If we took capital F prime, we would have 2x over 2, and then minus 1, which certainly simplifies down to just x minus 1, which is the function that's inside of our integral right now. So that works. So let's go ahead and find it with the fundamental theorem of calculus. We want to do capital F at 4, that's our upper endpoint, subtract capital F at 0. We'll evaluate both of those. So capital F at 4, we could say is going to be 4 squared divided by 2 minus 4. And then we'll subtract the evaluation at 0. Well, this is just going to get me 0 over 2, subtract 0. So that actually is not going to contribute anything to the problem there. So the final result here we can get is just going to be 16 divided by 2, subtract 4. This is all going to go to 0. Then we have just 8, subtract 4, or just 4. So there we have it. So just a 4 there. So let's go ahead and verify this one by just considering what's the area under the line y equals x minus 1 from 0 to 4. I think this would be a good exercise to kind of consider what we just found. We'll try working with a graph here and consider, again, the interval from 0 to 4, and I'm going to try to plot this line. So first, if I wanted to graph a line y equals x minus 1, I can find its intercept. That's going to be at -1. So we'll have an intercept at -1. And then we'll plot out 1, 2, 3, and 4. That's my interval from 0 to 4 there. And since our line here is just a slope of 1, we know it's also going to go up 1 for every rise 1 for every unit of run. So 1 up, 1 over, all the way across. So we'll plot that. Here we go. And so when I evaluate at 4, we should get a height of 3 here, this top point right here. So approximately something like this. Where our top value here is at 4, 3. So let's notice what we have. We have some area that's actually trapped below the x-axis here in this little region. We'll fill in. We'll kind of paint that red. And then we have some nice area accumulated above the x-axis. We'll give that some blue. So let's go ahead and consider, just with the area that we have, see what the total integral here should be. So this is at x equals 1, where we have that changeover. Looks like that small red triangle gives us really a 1 by 1 triangle, which gives us really a negative 1/2 in area. So it'll contribute negative 1/2 to the integral itself. The blue triangle here we know has a height of 3. So this has a height of 3 and also a width here of 3. So it's a 3 by 3 triangle. And so a 3 by 3 triangle would give us 9 halves for its area. 3 times 3 divided by 2. And so 9 halves positive for the area would be added to the negative 1/2 area that's in red. So if we add these together, it looks like we'll get 8 halves, or again 4 units of area here, which is exactly what we found when we considered the fundamental theorem of calculus. So in this case, it was easy enough to kind of algebraically work through the area underneath this line, accounting for the area above and below the x-axis. So this checks out with our fundamental theorem. Let's go ahead and consider another graph here. So using capital A of x as the integral from 0 to a of the function f of x dx, where f of x is shown in the graph below, we want to consider determine the approximate values of a that would result in a local max for capital A of x. So we want to consider here, where is our actual area, the accumulated area, going to be at its maximum? So there's a couple ways to consider this. One is just to consider f here as some velocity function, because we're going to be integrating that to some accumulation function. So one way is just to consider, again, f of x, the function in the plane here, is some, you can consider, rate function. So we know that whenever our rate goes from a positive to a negative, that creates some maximum. So one way is to just consider, where does this rate function go from a positive to a negative value, or a go from increasing to decreasing there. So one way we can do that is just to consider the accumulated area as we go. So if I consider, this would be all positive area accumulated under my curve all the way up till, let's call this maybe 3.2. So that value at 3.2, we have some accumulated area, and at that moment in time, notice that if we started to accumulate any more area, the next portion of our function actually accumulates negative area. So this is at a point in the function here that we actually reach a maximum amount of accumulated area in that neighborhood. So x equals 3.2 looks like a really good candidate for this result. We can also see that this rate function goes from positive, it's above the x-axis, to negative in this section. So the actual function drops below the x-axis. So we know that whenever our rate function or our rate of change goes from positive to negative, that creates a little maximum value. So whenever we go from positive to negative, that critical point there is going to be a max. So that matches up with what we should see there with 3.2. So this next little section, we know we're going to be creating some negative area accumulated here. We'll accumulate some positive area again once we hit, let's see, about 6.3 here. At this value, we'll have some more positive area accumulation. And then finally at, we'll call this maybe 9.4, we have another section of negative area, and it looks like it kind of carries on for the rest of the graph. So we'll put that in right in here. So if I was to look at seeing where we, another point in which we might have, again, a maximum area accumulated, it looks like right after this big blue section again, this another positive section at 9.4, that's another point in which we will have kind of this local maximum of area accumulated so far. We've passed through the negative portion. We've accumulated all the positive area we can by 9.4, and we're only going to accumulate negative area after that. So at 9.4, we should have a maximum again for our function, 9.4, or our accumulation. This also checks out because our function here, our rate function, goes from a positive to a negative. Therefore, we're going increasing and then decreasing in terms of our area accumulation. So those 2 points. If I considered where I might have a local minimum for my area accumulation, a local minimum, well, that's going to be found right after I've picked up as much negative area as possible. So consider the point 6.3, x equals 6.3. We've accumulated some positive area for sure, but the negative area that we've accumulated is really maximized when we hit 6.3. So we've accumulated all the negative area that we can, and we're never going to be smaller in our accumulated area than at 6.3, going from left to right. So this is also a point on the function where we go from a negative rate to a positive rate. So if we go from a negative rate to a positive rate, that's again creating a minimum value for us. So at 6.3, we can say that accumulation function is going to be minimized. And I think that would be our result for those. We can take a look at the fundamental theorem of calculus part 2 here. This definition states if f is a continuous function on interval a to b, then the integral function a is defined as a of x is equal to the integral from little a to x of f of t dt. And we could say that a prime, capital A prime, is equal to the derivative with respect to x of the integral from a to x f of t dt, which was equal to just the f of x function. So this a of t function, again, is measuring the accumulated area under the f curve on this interval from a to x. Again, a is some fixed value, some constant, and x is some unknown second endpoint. So if I consider the function here, f of x, which is equal to the derivative dx of the integral from negative 2 to x, t to the fourth minus 3t dt, we can consider applying the fundamental theorem of calculus with this integral. And I'll kind of walk up the long way for this. We could say that the f of x could give us the derivative of the integral here, which ends up being just our function itself evaluated at my upper endpoint here. So this would just be evaluated at x to the fourth minus 3x. One reason why this is true is the following calculation. If I needed to take the derivative of an integral, let's walk through the kind of the details of why this would be true. Based on the fundamental theorem of calculus, we could actually simplify this expression. The integral itself, we could say, would be the antiderivative. We could call this capital F, evaluated at x, minus capital F, evaluated at 2. So the antiderivative of our function evaluated at our two endpoints. Now, if I took a derivative with respect to x of these two antiderivatives, well, distributing this derivative to capital F of x would just simply give me f of x. That would be by definition, if I took f prime, capital F prime of x, that's equal to that original f of x, little f of x function. If I take a derivative of f at 2, notice that this is just a constant. If I evaluate any function at a constant, it's just going to give me back this constant. So if we have a constant here, this would actually just subtract 0, because whenever we take a derivative of a constant, it just becomes 0. And so this gives me back just f evaluated at x, which in this case is just my original function here evaluated at x. And so that would be our final x to the fourth minus 3x, because this is our f of t function. So we're taking that same function, just evaluating our endpoint at x. Part B considers just f of 5. We can evaluate here 5 to the fourth minus 3 times 5. If we consider doing that, we'll have, looks like 625 minus 15 for that calculation for us. And looks like that's going to be 610 when we're done. 5 to the fourth minus 15. And then we can finally find just f prime of x, little f prime of x, which in this case would be just 4x to the third minus 3. That would be the final result. Let's consider keeping with these antiderivative functions and considering the graph below. Suppose that we have capital F of t has a derivative of little f of t, shown below, and capital F of 0 is equal to 2. We want to find each of the values based on our function here in our graph. The first one we'll try to find is capital F of 2. So let's consider how we would consider capital F of 2 and relating that to the known information of capital F of 0. So if I wanted to consider what expression we could put together to take what is known and find the unknown, well, a way I can actually express these two antiderivatives is with an integral. We note that the integral from 0 to 2 of the little f of t function, which is shown below, this is our little f of t function, dt is defined by, well, it's the antiderivative at 2 subtract the antiderivative at 0. So this gives us a way to relate this capital F of 0 to capital F of 2 in an equation using our integral. So let's take a look and see what we know so far. I know certainly f of 0, capital F of 0 is 2, and I also can find out what the integral here is from 0 to 2. I know I can find that with the area underneath the curve from 0 to 2. So let's take a look at that. From 0 to 2, it looks like we have some shapes that we could figure out here. First off, we can consider there is one full box of area. It looks like a 1/2 of a box of area on top of that. And if we look at the other triangle that's formed on the left side, that larger triangle is a 1/2 triangle, which in total looks like we'll have, again, 1 unit of area for that triangle there. So it's a 1/2 triangle. 2 times 1 divided by 2 is just going to give me, again, 1 unit of area. And then that will be it for that section from 0 to 2. So it looks like we have 2.5 units of area here from 0 to 2 to get started. So we'll just call that 5/2. 2.5 or 5/2 would be equivalent, is going to be equal to f, capital F of 2, we do not know, minus capital F of 0 happens to be 2 itself. So to solve for our capital F of 2, we can add 2 to both sides. And if I consider adding 2 here, this is actually going to be the same as 4/2. So this would be the same as 4/2. So our total here for capital F of 2 is going to be 9/2. 9/2. Or we could call that 4.5, either way. So 4.5 would work. Okay, let's do the same idea with f of 7. We could set up an integral again to relate the known capital F of 0 to capital F of 7. So the integral from 0 to 7 of our f of t dt is equal to the antiderivative at 7, subtract the antiderivative at 2. At 0, excuse me, at 0. There we go, which is equal to 2. So now let's go ahead and see if we can solve for that definite integral using the area underneath this curve. So we already have from 0 to 2 mapped out, and we can keep filling in our results here for each of these sections. I want to go all the way to x equals 7. So all the way to this line. So let's keep going from left to right. It looks like we'll have another 1/2 box of area above the x-axis. Looks like all of this area here is going to be positive. If we add that up, looks like a total of 3 units of positive area up top. And then the rest of this is actually going to be area accumulated under the curve, which we know should be negative. So let's see what that accumulation would be. First, I'll just kind of take a slice here at 4. Notice that this is a triangle created underneath the x-axis, which has a height of -3 and a width of 1. So it looks like we'll have -3/2 units of area in that section of the triangle. And then we are left with a square here, -3 by 3 units of area. So negative 3 by 3 would give us negative 9 units of area in that square. So putting those all together looks like we'll have 3 minus, we'll have negative 3/2 or 1.5, and then minus 9 units of area there. And when we put that together, it looks like 3 minus 10.5, or we can say that is negative 7.5. Negative 7.5. So that's the area for that integral itself. So we'll put that in, negative 7.5 units of area. And then we have our capital F of 7 is unknown, and then minus capital F of 0 is the 2. So to find our result here, we'll just add 2 to both sides, and we should have what we need. And it looks like that'll give us negative 5.5 for capital F of 7. Negative 5.5. All right, so we've got the antiderivative evaluated at each of those values of 2 and 7 using the fundamental theorem of calculus there. The last problem that we'll consider is just taking a look at some integral properties and seeing how we can work through this. So we are given 2 integrals, one for the function f and one for the function g. And this is going to take a look at kind of what we would call linear combinations of functions here. And I'm going to try to apply an integral to this linear combination of functions. So let's start with just considering how the integral kind of moves throughout this linear combination. Here's our problem. We want the overall integral from 2 to 7 of the function 3 times f of x minus 6 times g of x dx. So there's, again, a linear combination of functions inside that bracket that we want to evaluate. And we know the individual integrals of each of those functions. So let's consider how this would work. We want to pass our integral through, and whenever we see a constant here, we can actually split this up, and we can also split our integral at sum and difference points. So we could say that this would be equivalent to the integral first from 2 to 7 of 3 times f of x dx subtract the integral from 2 to 7 of 6 times g of x dx. So I can split this integral again to both terms of the difference with the 3 f of x dx and 6 g of x dx. So I can split at that point. 2 integrals there. I can also consider these constants. These constants can be moved inside and outside the integral as I please. And so one of the properties we can execute here is that this would be the same as 3 times the integral from 2 to 7 of f of x dx minus the 6 brought outside the integral because it's a constant, 2 to 7 g of x dx. So here our linear combination of functions we've actually separated and we've also pulled out those constants. So now with what we have left, I notice that I do know the integral from 2 to 7 for the f of x dx function. That's 8. So we can replace that with just a constant 8. Subtract 6 times the integral of the g of x function on that same interval happens to be -5. And that's known to us. So we consider that as just a table value. So we can multiply that constant 6 times the -5. So to finish this up, we would just have the product 24, and double negative would give us a plus 30, which is going to give us 54 as the total. So this gives us just a walkthrough of how we'd work with linear combinations inside a integral with some integral properties. So just to highlight a couple important integral properties for us, one would just be the sum and difference rule, where we can consider that a integral from, let's say, a to b, just write it in general, of a function f of x plus some g of x function, again, added or subtracted, so you could put the plus and minus, dx, we could rewrite this integral as follows: the integral first from a to b of f of x dx, add or subtract the integral from a to b of g of x dx. That would be just a sum and difference rule, where we can separate that integral into two parts. Another thing that we could do is just a constant multiple rule. So if I have that same integral, some a to b, where those are constants, we can consider just a constant, call it c, times a function f of x dx. And that constant as well can just be moved outside the integral, and we can say this would be c times the integral of a to b of f of x dx. So constant multiplier rule and a sum and difference rule could be helpful when we were walking through our definite integrals in the future lessons. So thanks for watching this video, and hope to see you in the 3.3 lesson, where we'll walk through how to take more definite integrals and indefinite integrals in chapter 3.3.